Now that we know how long each engine cycle takes, we can calculate the injector pulse width we need to achieve our target air-fuel ratio. We can start by calculating the required injector duty cycle using this equation. Here, the injector duty cycle is simply the required fuel flow divided by the total fuel flow and then multiplied by 100. Earlier, we calculated that we needed 0.462 pounds per minute of fuel, and the injectors can flow 1 pound per minute total, so let's put these numbers into the equation. Solving the equation gives us an answer of 46.2%, which means that our injectors need to operate at 46.2% duty cycle to supply the correct amount of fuel. The ECU doesn't work in duty cycle though, so let's go through one last step and see what this duty cycle is when expressed as a pulse width. To calculate pulse width, we need to account for the cycle time, and we can do that with this equation. In this equation, the injector pulse width is equal to the cycle time we worked out in the last module, multiplied by the injector duty cycle we've just calculated. We know that our injector duty cycle needs to be 46.2%, and we calculated the cycle time to be 20 milliseconds. So if we put these numbers into the equation, we get an answer of 9.24 milliseconds. So this is the final result that the ECU will calculate, and now we have an actual injector pulse width that can be sent to the injector. We started off with a measured airflow value, corrected it for air density to calculate mass flow, and finally calculated the injector pulse width we need to achieve our target air-fuel ratio. I'll mention at this point that we haven't taken into account the dead time of the injector, and the 9.24 milliseconds we just calculated is the total time we need the injector to supply fuel for. The ECU would add the dead time value to this calculated pulse width, and this is what would be supplied to the injector. Now let's take this one step further and test the result. We put the engine onto a dyno, run it at 6,000 RPM, and we ensure the ECU is delivering a pulse width of 9.24 milliseconds to the injector, and we measure the air-fuel ratio. Remember that we're calculating the required pulse width to achieve an air-fuel ratio of 12.5 to 1, but on the dyno, instead of the 12.5 to 1 we expected, we actually measure 11.5 to 1. So let's talk about why the engine is now running richer than we expected. The reason for this is that we made an assumption right back at the start of our calculations. We assumed that the engine was operating at 100% volumetric efficiency, or in other words, completely filling its cylinders on each engine cycle. Chances are that this isn't going to be very realistic in many instances, and the VE may in fact be much less than 100%. Instead of the 5.77 pounds per minute of mass airflow per cylinder that we calculated, in reality the engine will actually move a little less than this if it isn't reaching 100% VE. All is not lost though. Let's look at how we can correct the air-fuel ratio really easily. If we know what the actual air-fuel ratio is, we can very easily calculate a correction factor, which we can then apply to get the fuel delivery right back where we want it. The equation is shown here, and all we need to do is divide our measured air-fuel ratio by our desired air-fuel ratio. Putting the numbers from our example into this equation, we get a correction factor of 0.92. What this means is that instead of operating at 100% VE in our example, the VE was actually 92%. This is why the engine was operating with a richer air-fuel ratio than what we expected. In the next module, we're going to have a look at how we can correct our fuel delivery quickly and easily using the correction factor we just learned about.